In this video, we will talk about the paired samples t-test. The paired samples t-test is a statistical test for two sample means, but in this case, the two samples must be paired. This means that each value in one of the two samples or groups corresponds to exactly one value in the other sample or group. This makes the two groups paired and essentially dependent on one another. The paired samples t-test does not directly test the means of the two groups. Instead, it tests that the mean difference between sample pairs is not zero. So because of the pairing, we're interested in the differences per pair. In other words, this test tests the hypothesis that the paired differences are not sampled from the null distribution. The null hypothesis then is that the mean difference is equal to zero. If the mean difference is equal to zero, then the two samples do not differ. Let us work through an example to see how this actually works. The example concerns the familiar hypothetical situation in which 20 children are administered an intervention, and each child is tested before and after the intervention on the same test. Therefore, we have two scores, and the question is there a difference between the before and after scores? As we've said before, this is a horrible way to test the intervention from a methodological point of view, in part because scores increase just by retaking the test, and you can draw no conclusion without a control group. But here, from a statistical viewpoint, it's just two dependent samples. They're dependent because although there are two sets of values, there is the same children that have values in both samples. It's not two different groups. It's one group of children, and each child has a score in each sample, in the before and the after. So the two samples are paired. Still, from a variables point of view, again, we have a quantitative variable, which is the score on the test, and is our dependent variable, is the one that we want to see if it is affected. And the independent variable is the time the test was administered. So before versus after the intervention. These are the two values on our qualitative or categorical independent variable time. If we look at the box plot for this situation, we can see that there is a before sample, here is the set of values, and an after sample, the other set of values. But this is a bit misleading in the sense that they're not different children. So we could conceivably draw a line for each child, connecting the child's before score with their own after score. I have jittered the lines a little bit so they're all visible and do not fall completely on top of each other. But in general, you can see how different children have slightly different trajectories. So here are some children that did not change in score at all. There is a child that changed by 2 points and a child that changed by 2 points in the other direction, so getting a lower score after than before. Most children gain maybe 1 point, and so on. So this is the graphical situation showing the individual children's changes. And this is a list of the measured data. These are the scaled scores before and after. And from each pair, which corresponds to one child, we can calculate a difference. So for the first child who got a score of 3 before the intervention and 4 after the intervention, the difference was +1. There was one child who got a lower score after the intervention than before, and for this child the difference is -2. These are the differences we can work with. And in fact, we don't need the original scores anymore because the paired samples t-test is identical to the one sample t-test on the differences. So by subtracting the after minus before, we have created a new data set, which is the set of differences, and all we need to do is run a one sample t-test on that. This is what the paired samples t-test is. The null hypothesis for this test is that the mean difference is equal to 0. So the reference value for this one sample t-test is 0. We are comparing the difference scores against the reference value of 0. So we are testing the hypothesis that there is a non-zero average difference. The mean of these difference scores is 0.85. The standard deviation of these numbers is 1.14. There are 20 children, and therefore the t-value is the mean divided by the estimate of the standard error, which results in a value of 3.34. This is our t-value. How many degrees of freedom are there? Well, there are 20 children, so 20 different scores. And we calculated their mean. That's one sum. So 1 degree of freedom less than the sample size. N minus 1 is the appropriate number of degrees of freedom for the one sample t-test and for the paired samples t-test. But here n is the number of children, which is equal to the number of differences. It's not the number of original measures because those are gone. So there's 20 children. Each child was measured twice. We had 40 original data points, but we only have 20 children, 20 differences, minus one sum, 19 degrees of freedom. Our sample size here is 20. And the p-value for this t-value and this number of degrees of freedom is 0.003. This means that we can reject the null hypothesis that the differences are equal to 0, and we can conclude that the after and before scores are not equal. The effect size for this intervention is given by dividing the mean by the standard deviation, not the standard error here, the standard deviation. This is Cohen's d, and it shows us that the effect size of this intervention is 0.75, so 3/4 of a standard deviation advantage for the after intervention scores, scaled scores, compared to the before intervention scaled scores. And the correct way to report this result is the same as for the one sample t-test. So the t-value, number of degrees of freedom, and the p-value without a leading 0 and 3 decimal places, and optionally the effect size and its 95% confidence interval. This confidence interval for D runs from a positive to a positive number, so it does not include 0, and that's why the difference is statistically significant, because a 0 effect size is not included in its 95% confidence interval.